we most of the approach is fixed focus, because location of the poles in the complex domain is easy. And once you have a location of the complex, the conjugate poles in the X domain, you can calculate omega n and zeta. So that means we could have more flexibility in doing the system, in kind of treating the system dynamics in the time domain. So most of the strategies is starting from the time domain. And here, this is a very typical response of the second order system to the unit step input. Again, the demonstration here we try to illustrate is in response to the unit step response. Hopefully, you learn the techniques. You can try to develop your tools for the system response to, say, other type, for example, unit ramp or unit impulse. Okay, so keep in mind, if you like, and in your notes, you highlight this one. That is here from this page onward. We're going to talk about the system categorizations, is in particular to the unit step response. Okay, and that is a scenario. So this is a typical curve, and we see in this curve you pretty much have a good feelings. And again, the system will oscillate, and assuming the system is underdamped. If the system is overdamped, then that'll be a different story, and we won't cover it here. And from here, you can see this oscillating. Eventually the system going to converge, approaching to certain steady state values, and the approaching process will take time. Depends on the system's features. The approaching time will be short or long, depends. And so here we use the certain tolerance. For example, we say if the system's the output response is falling into, say, 5% or 2% of the command values, then we say the system pretty much enters the steady state, the period. Okay. For that one, we denote once the system's oscillation is within that kind of tolerance, the time we define as the TS. S means settling time. The S means settling time. So on the page today, I give you pretty much, you can gradually put the notes on the handouts I give to you. And on today's handouts, there are 3 figures, and black one are from my lecture notes. The good, colorful ones, the few colorful figures are from our textbook. Okay, and they pretty much the same but different, little bit different symbols. Our textbook using capital, and my lecture notes using the lowercase. And okay, and again, those 2 figures from our textbook is from, if you like, you can put a note from section 5.3. So that kind of provides you, if you like to have more readings. Okay, so now I introduce the first one, the first index to categorize the system dynamics. This one is from the settling time. Okay, and now we move on to the more the initial, the beginning. So, for example, the system is underdamped, and we know the system will try to catch up the command. So he will try to rise his value as soon as possible, which means in terms of its damping ratio and the natural frequency, we'll try to reach the value here, but it's overshoot. It's got too much momentum from the beginning, so it's kind of the running. If there's a wax here, then we stop, and then coming sliding forward and coming back, right? Okay, so the same feeling like this one. So from here is we say this is an overshoot. Okay, so here again, that is another keyword. We say as long as the value is over the command, we say that's overshoot. And this one, the maximum value of the overshoot is called MP. MP is the magnitude of the peak. And also, we know that when is the first time the system response reaches the value of the command. So here it's called TP, TR, okay?
Right.
And TR is called the rising time. And rising time, here you have to know the memorize the definitions. And this is a very common definition. And TR basically denotes the time for the first time the value the system reach the command, and that defined as a TR. And TP basically is the time when the system got his peak time, the peak. So TP is called the peak time, or whatever the similar term the peak appeared in that kind of definition, that is called the peak time. And the other one is called the TD. TD, from this definition, you can see TD basically denotes the time when the system response for the first time to reach the 50% of the command. So that corresponding time for the TD. D is for delay time. Basically here, this TD provides us more kind of the transient measurement of how quick the system rising up. Okay. And the reason why I provide you the handouts here today is about additional terms, and I will point out that one later on. So if you compare the first two figures carefully, our textbook provides one additional index who can tell what is the additional one between the first and the second figures. PR1. Okay, so that will be the additional index, and that is for my first one. That is my first one to say it. And so I kind of I just prepared this handout this morning. So that's the reason why I prepared this one. So I will provide you the TR1, and that's just a quick formulas here. Okay. So in majority, we will talk about the formulas to quantify those kind of the indices. So again, as long as you can identify those indices, you pretty much uniquely define the system response. In turn, you define the omega n, you define zeta, the damping ratio. On the other side, if you are given the omega n and damping ratio, and then you should be able to quickly calculate your response, the response of your system to unit step input. And once you have those kind of curves be built up, you can right away to measure those parameters per those definitions here. So kind of the two ways to do it. So here we do this one by one, and the first one we define the peak time. And peak time by formula, and again, that is my exercise, and I just did it this morning to my own copy of the handouts. I just write all the symbols, all the equations next to the symbols on the handouts. I feel this will be very useful because, believe me, later on, once we're doing the examples here, we have so many formulas you don't want to kind of turn over the books or the lectures page by page. So here, this one, you could just write the equation next to the symbols or appropriate places on the handouts. And that will be your kind of cheat sheet. I would say cheat sheet for the future. So before I introduce the method, you can write it down. The TP basically is pi divided by omega n and 1 minus zeta squared in the square root. Okay.
Is that only for this system, or is
only?
it
Yes, I want to emphasize.
Because you have an n, right?
Yeah, this only for second order system in response to the unit step input.
So when n is
what is it?
equal, you have n.
And
And n is equal to 1, right? Yeah.
oh,
So
this
when
one
would
only. This one is only occurred for the first peak, for the peak. Basically, the peak, the maximum amplitude will only occur at the first one because it's decaying, right? So only we say this is never mind. Get away this end. The end, that means don't confuse you. If you like, you can scratch this kind of wording. Not important. Okay? Not important. The way we can try to calculate this is using this equation here. So as long as you have the symbolic calculations of the curve, then for example, we say this curve is equal to CT. So we simply take, if we want to find this value here, then we simply take the derivative equal to 0. That is from calculus, finding the maximum value and the location of the maximum value. So from here, I believe because the C is in waving, has a waving features. So that means the C has a waving features. If you try to solve for that one, I can tell you here. So here is the kind of the waving functions here. So if you're going to solve for CT, dCT, dt equal to 0, then you will have the multiple.
You're gonna have each
multiple roots. And here is a 1, here 2, here 2, and 3, and all the peak, all the there, okay? So the multiple roots, and then that is what I mean here. We only concern about the first one, and that what I mean is, I think I'm going to change to multiply my node. I should use other parameters, say P, because I don't want you to confuse n with our omega n, this n. The two are irrelevant.
Well, I wasn't confused about that, but I was
anyhow, yeah.
Okay.
So here, basically, this one denoting is the which root. So here we have a multiple. We pick the first one. Okay, that's an n. What I mean n here. Okay. So if you repeat that one, and again, this formula should be based upon the parametric the formulations, and what is the parametric formulation of C? If you remember from the beginning, our lecture starting from is here. We have the transfer function s squared plus q zeta omega n as omega n squared, and then we come into the unit feedback system. So this is our RT. Okay. So for this one, this is a closed loop. So this one will be equivalent is the C s over R of s equal to s squared plus q zeta omega n s plus omega n squared. This is our transfer function of this system. And Friday last week, I was being very merciful and kind. I didn't show the calculation with the symbol, but instead I with other parameters. I think is this one, right? Whatever the numerator, right? Remember? So I think 1 or 2, whatever. So Friday last week I demonstrated is these questions, and I repeated saying that, and if we can work on the numbers, then you should be able to work on the parameters here. Okay, and so for example, when we do the unit step input, so the CS will be equal to omega n squared, s squared plus 2 zeta omega ms plus omega n squared times 1 over s, right? Then you do the certain step, then you should be able to find the CT equal to something. Right, and what is that something? And CT corresponding to this case is this one. And I think this equation has been showing in the previous few pages that appeared. I write it down, use it. Oh, that's it. 1 minus
You got this.
exponent minus zeta omega np. I forgot this amplitude here, I will leave it blank. And times sine zeta, sine omega n, 1 minus zeta square t plus certain phase angle. Right?
Yeah.
We have this form. Let me think of it. If you don't mind, let me go back to the previous slide to find out. Number 15.
Stella's got your back.
Yeah. Okay, so the number 15 here, we already have this equation here. So let me
Huh?
okay. Yeah, so that is here. Okay, so that is this equation. This equation corresponding is this one is what we're going to calculate this one here. Okay, and if you are curious how can we do it, you can give a try. And then you show me your calculations. If you can, it doesn't matter, you can reach it or not. You show your calculation, then I will give you 1 copy of the process. How about that? If you are interested in how to do this one, how to do this one, then let me know. Okay. But anyhow, we have the CT or our response like this. Then simply we take the derivative equal to 0 upon this equation. Then you should be able to find those multiple solutions here. Okay. So. Okay, so that is the calculation history. But again, here we are not concerned about how to reach the result, but we want to know how to use the result. So here I quickly showing you the detail. He can show you the detail, but here, okay. So that is a peak time. And then once we know the time TP here. So this is the TP. Then who can tell me how to calculate NP? What is NP? NP is the magnitude between the value and 1. So here, anything? It's good. I heard about something. CTP minus 1, right? Okay, so that is NP. Will it be straightforward? Okay, and so for NP, that'll be the next page. And so here again, we calculate the maximum value of the system response minus 1. That gives us the NP. So NP basically equal to this one, and sometimes this number. Okay, if you like on your handouts next to NP, you can write it down these equations. NP equal to this one, exponent of minus something. Minus, let me read it out. Let me write here. NP equal to exponent of minus pi zeta times 1 minus zeta square. Okay. So again, if you like on the handouts, you can write that equation next to the symbol. And for these equations, I can tell you for any zeta, because here we studying is the underdamped system. So for any zeta less than 1, I can guarantee this number is always less than 1. So for example, say you might have the number say 8.8, and sometimes people like to use percent, so that's 80%. So if we are using percentage of the peak, then we simply multiply, we scale up by 100. Then in this way, this number will have the unit percent here. You got it? Basically, if say this is the 0.8, then if you like, you can express say 80%. That's it. Okay. So basically, this 100 is nothing new. We just scaled up in terms of the unit of percent.
So your overshoot will always be less than 1.
We overshoot and
Well,
when
Okay.
Whenever the system have an overshoot, that corresponding is the underdamped system. If the damping ratio is less than 1, then always have the overshoot. Hopefully, I want to look at the curve. This one. So from here you can see this one don't have the overshoot 1. Yeah, I think my impression is right. If the system command, how many of you are taking vibrations? Raise your hand. Okay, I'm going to write down your name. Thank you. What is the definition of the underdamped system? Zeta less than 1.
Yeah.
So don't try to confuse me. Yeah, because right now many things has been into my intuition. To respond to the questions, I just quickly from my intuition without any detailed technical thinking. You try to confuse me, yes. For the damping ratio less than 1 is always have the overshoot. And maybe since we are here, we can see the magnitude of the overshoot basically governed by the. So say for example, if we only want to have say the 20% of less than 20% of the overshoot, so basically this curve corresponding to is how much? 0.5. So that means you better to have the 0.5 or 0.5, 0.45 something, then it's guaranteed the overshoot is less than 20%. Okay, so yeah, so that is for this one. Okay, so that's about the overshoot. So we have done this. So we have peak, we have overshoot. Then next one. This basically provide us more kind of the tables to look up the value quickly. So either use that equation, you can precisely calculate the zeta, or you can precisely define the relation between NP and the zeta. But this curve sometimes can give us quicker. Say if you have the damping ratio, you can quickly look up to what value of the percentage overshoot here. Okay. Sometimes if you're lazy, a little bit lazy, you can look up this one. Sometimes I use this curve to roughly identify the value quickly. Okay. And it wouldn't make a difference too much. Okay, unless in the homework or in the test I require certain precision and the otherwise. Okay. So again, this curve corresponding to that system, corresponding to this that kind of system in particular. And next one, again, we want to look up the TD and TP. So TD and TP, and TD